L'Hopital's rule is just a rule for evaluating limits when we can't just plug in what we're trying to, the value at which we're trying to evaluate the limit. So if f and g are both differentiable functions, and f and g both are equal to 0 when x equals a, to take the limit as x approaches a of f of x over g of x, we can replace that with the derivative of f over the derivative of g, and then try to plug in a. The idea is when we try to plug in a, our favorite way to calculate a derivative is to just plug in the numbers. But when we try to plug in x equals a, we get 0 over 0. So L'Hopital's rule says let's take the derivative of the top and the derivative of the bottom, and then try plugging in again. So take some derivatives and then plug in. So let's look at an example. Let's look at an example. No, that's not the section I wanted. Strange online textbook behavior. I'm going to need more space. Let's suppose that we wanted to calculate the limit as x approaches 0 of e to the 2x minus 1 over x. If we try to plug things in, if we just try to plug in 0, we end up with 0 over 0. So in this case, I'm calling the top f of x will be this e to the 2x minus 1 in L'Hopital's rule, and g of x will be just x. So notice that the numerator and the denominator are both differentiable functions, but if we just try plugging in 0, we end up with 0 over 0. So f of 0 over g of 0 so we get a 0 in the denominator. That's not always bad if the numerator is some finite value. Then we can say this is going towards infinity. But unfortunately for our heroes, we have e to the 2 times 0 minus 1. So f of 0 over g of 0, e to the 0 is 1. 1 minus 1 is 0. So we have this 0 over 0. We can't just plug in to evaluate this limit. Oh, we're not shocked by that. It's an example from L'Hopital's rule. We're just kind of like bummed. We can't just plug in to evaluate this limit. So we can apply L'Hopital's rule since the numerator and denominator are both differentiable, and since when we do plug in, we get 0 over 0. The numerator at 0 is equal to 0, and the denominator at 0 is equal to 0. It's important to note that 0 is the a in this case. So everywhere L'Hopital's rule said a, this problem is saying 0. So it's not, this 0 is not these zeros over here. This 0 is the one that's going into the functions. So L'Hopital's rule to the rescue. Let's look at f prime of x and g prime of x and evaluate those functions. So f prime of x f prime of x is 2e to the 2x, and the derivative of 1 is 0, and g prime of x is equal to 1. So the limit as x goes to 0 of e to the 2x minus 1 over x is equal to, according to L'Hopital's rule, the limit as x goes to 0 of 2e to the 2x over 1. So that's using L'Hopital's rule. Not taking the derivative of the expression, just separately the numerator and the denominator. But now we can just plug in values. Now we can let x go to 0 by plugging things in. And that's what we wanted in the first place. So 2e to the 2 times 0 is 2, so e to the 2 times 0 is e to the 0, which is 1. 2 times 1 is 2. Divided by 1 is 2. So here we're able to use L'Hopital's rule to evaluate the limit because it gave us a 0 over 0. Any questions? And we can verify that looking at a graph of this function, which if I just asked you to calculate this limit in the first place, since we can't just plug in, instead of using L'Hopital's rule, since we have such great amounts of graphing power at our hands, we can just evaluate this when x equals 0. Oh, come on, let me get the y-intercept. Oh, wait, it's undefined at x equals 0. But we can't evaluate it when x equals 0, but we can easily evaluate it near 0. I probably wouldn't ask for a L'Hopital's rule question on a quiz, because I'm already asking questions about, can you take some derivatives? And more important than using L'Hopital's rule to evaluate a limit is thinking about what L'Hopital's rule is telling us. So if we go back to this, when we try to plug in x equals a, we get 0 over 0. So what's important is not that these functions, the numerator and denominator, are both going to 0. The question is, how are those two functions going to 0? Because sometimes 0 over 0 will be infinity, sometimes because the denominator is going to 0 faster than the numerator. It could be that the numerator is going to 0 faster than the denominator, in which case the limit is going to be 0. So in that case, 0 divided by 0 is going to be 0. Sometimes they're going to 0 at just the right rate so that they meet up and we get 0 divided by 0 and we get some finite value. If we think about the example that we had before, or this example here, and we modify it just a little bit. No, I don't want to do that example. Any questions? Comments? Snide remarks? I was about to modify this one to an example that doesn't actually do what I wanted to do. So All right, let's pause the video here. Oh, let's actually mention other cases where L'Hopital's rule works. So L'Hopital's rule is not just 0 over 0. Zero over 0. There are other indeterminate forms. So 0 over 0, infinity over infinity, zero times infinity, which is just a variation on 0 over 0. And all the variations of these, it's useful for things like infinity minus infinity. Because sometimes infinity minus infinity is infinity, sometimes infinity minus infinity is negative infinity, and sometimes it's a finite amount. Other examples, 1 to the infinity, 0 to the 0, and infinity to the 0 power. Most of the famous 1 to any power is equal to 1. And then what if it's 1 to an infinite power? Or 0 to the 0, or anything to the 0 power is 1, unless it's 0 or infinity. So these are all the cases where L'Hopital's rule can come into play. But for the most part, we have a lot of computing power. We can just look at a graph of the function or plug in large values of the function if we've got limits that are going to infinity.
What does a derivative of infinity look like? What do you mean by a derivative of infinity?
So I'm not really taking the derivative of infinity. I'm looking at the derivative as it goes to infinity. So when I'm talking about 0 over 0, a variation of this would be if when we try to plug in infinity, and this is just going to infinity over infinity. That's this case here. We can try to calculate that limit by looking at the derivative of the top and the derivative of the derivative of the numerator, the derivative of the denominator, and then looking at the limit as x goes to infinity again.
Can you do an example of an infinity problem?
So let's take a look.
Please, thank you.
Yes. Let's take a look. Let's suppose we have the limit as x goes to infinity of 5x plus e to the negative x over 7x. So in this case, our f of x is going to be just the numerator, 5x plus e to the negative x. And our g of x is just 7x. When we try to plug in large values of x, so when we think about x going to infinity, we end up with infinity over infinity, and then this e to the minus x goes to 0. So we've got infinity divided by infinity. Both of these functions are differentiable. We have an indeterminate form when x goes to infinity, so let's try L'Hopital's rule. So L'Hopital's rule says, well, if we separate this out, the limit as x goes to infinity of the numerator that goes to infinity. And the limit as x goes to infinity of the denominator, I want to associate this infinity down here with the one from the limit, but of just the denominator also goes to infinity. Both of these limits don't exist, but we end up with infinity over infinity. And that looks like a job for L'Hopital's rule. So the limit as x goes to infinity of 5x, the numerator, 5x plus e to the negative x over the denominator, 7x. I can replace the numerator and denominator with their derivatives. In this case, f prime of x will be 5 minus e to the minus x, and g prime of x is just 7. So now we know we're well on our way, because now the denominator just looks like a 7. And the numerator looks like 5 minus e to the minus x. So now we can just, quote, plug in infinity. We're not really plugging in infinity, but now, as x goes to infinity, the denominator goes to 7, and as x goes to infinity, the numerator goes to 5 minus e to the negative infinity, and that's going to go to 0. So the numerator goes to 0 as x goes to infinity. So this limit is going to be 5/7.
Isn't that just where we just take the highest power in the top and highest power in the bottom and then figure it out that way?
We could do that way. We could say this e to the minus x is going to 0, so in the long run, it's not going to matter. But is that going to hold up in court? Judge Judy is going to ask us to justify that. And so we're going to say, well, Judge Judy, we'll just use L'Hopital's rule. And if you say it with enough authority, then she'll just go, ah, yes, of course. Because I'm pretty sure Judge Judy is not really familiar with this much math. Because she's a lawyer. I mean, why would she be? So this is this is L'Hopital's rule going with our thinking. Because when you say, well, just use the highest powers idea, that highest powers idea relies on L'Hopital's rule. So I guess the short answer to your question is yes, absolutely. Any other questions? Rad. Let's pause the video here. Talk about more questions.